Hello students, welcome back. I think this is gonna be the final video, the last video of the entire semester. We're gonna discuss De Moivre's theorem and its applications here. De Moivre's theorem goes kind of like this. Polar form r times cosine of theta plus I sine of theta to the nth power is equal to r to the nth power, no surprise there, times cosine of n theta plus I sine of n theta. Well, that's surprising, because cosine of theta plus I sine of theta to the nth power is rather complicated. You may have to FOIL it, 100 times, maybe 1,000 times? Absolutely crazy. But multiplying by 100 or multiplying by 1,000, that's easy. Now, what is the theoretical background of this? It's actually coming from complex arithmetic that we discussed in the previous lesson. The multiplication can be obtained by multiplying out the moduli and then adding up the arguments. Division is the opposite, dividing the moduli and subtracting the arguments. And here's a rough detail of a proof. Begin with z equals r cosine of theta plus I sine of theta and calculate z squared. R cosine of theta plus I sine of theta, r cosine of theta plus I sine of theta, and multiply them up. And we have r squared. And because of the property of multiplication, you have to add up the arguments. Theta plus theta, we end up with 2 theta. What did we end up with? We ended up with the proof of De Moivre's theorem for special case n equals to 2. By the way, when n equals 1, there's nothing to prove because left hand side and right hand side are the same. Now, what if we have z cubed? That's z squared times z. So z squared is r squared times cosine of 2 theta plus I sine of 2 theta, which we just proved. And z is r times cosine of theta plus I sine of theta. Now we apply the same principle here again. Multiply the moduli and then add up the arguments. We get r squared times r, which is r cubed, and 2 theta plus theta, we get 3 theta. What did we end up with? The right hand side of De Moivre's theorem for the special case n equals to 3. We just proved the case n equals 1, 2, and 3. Nothing to prove for 1, we just prove for 2, and then we just prove for 3. Let's do it just once more. You see the pattern, but just once more. Z to the 4th power is z cubed times z, and z cubed is this. We just proved it. And then this is nothing more than z, and apply the same principle again. Multiply the moduli and sum up the arguments. So multiply r cubed times r, that's r to the 4th power, and then add up 3 theta plus theta, we end up with 4 theta. We ended up with the right hand side of De Moivre's theorem for n equals to 4. You saw the pattern now. Repeat this, and you're going to get n equals to 5 z to the 5th power. And repeat this again, we get z to the 6th power. Again, we're going to get everything. This kind of proof is called recursive proof. And to be a little bit more precise, you'll have to use something called mathematical induction. If you're not familiar with induction, never mind. Now, what if n is negative? Well, I didn't write the proof here. It's left to the exercise for interested students. All you have to do is repeat this subtraction, division rule, the second principle over and over again, repeatedly, recursively. In the end, we have this De Moivre's theorem as here. Another way to express De Moivre's theorem is Euler's expression here. If you use this advanced expression of polar form, then De Moivre's theorem becomes really easy. R times e to the I theta power to the nth power, and apply just the exponent rule. Then we have r to the nth power times e to the I n theta, because we have base e, and then, okay, just the exponent rule. Now, how do we apply De Moivre's theorem? Well, let's begin with some warming up. Here's a simplest type of problem, and this problem is so simple that you don't really need De Moivre's theorem. You see, I can simply ask Mathematica to do this computation, and in an instant it provides the answer. So what's the point? Well, if you do something like this to the third problem here, for example, well, you don't get anything. Even if you asked Mathematica to simplify, not much. So you really have to use your brain. Well, let's consider the simpler case first. We're going to use De Moivre's theorem, so inside should be expressed in a polar form. 1 plus I, that's simple enough. Argument is 45 degrees, and the modulus is square root of 2. So we have square root of 2 cosine of pi over 4 plus I sine of pi over 4 to the 20th power. Applying De Moivre's theorem, we have r to the 20th power, which is 1024. And applying De Moivre's theorem here to the angles, we have 20 pi over 4, which is equivalent to 5 pi. Cosine of 5 pi is negative 1, and sine of 5 pi is 0. So what do you get? We have 1024 times negative 1 plus 0i, we get negative 1024. That was simple. Let's consider a little bit harder case. We have to do the same thing. Express the inside as a polar form and apply De Moivre's theorem. You can express the inside as polar form by taking the modulus and then doing the usual trick. Theta is, well, arctangent of y over x, and then let's see, in this case simply taking arctangent will be okay because the point is in the fourth quadrant. In any case, we have 4 plus cosine of negative pi over 6 plus I sine of negative pi over 6. If you apply De Moivre's theorem and then multiply by negative 5 to each angle, you get 5 pi over 6. And calculating this, 4 to the negative 5th power, we have 1 over 1024. And cosine of 5 pi over 6, sine of 5 pi over 6, you can easily find those out because they are basic angles. In the end, here's the expression, the final expression. If you know how to use your brain, you can use Mathematica to check your answer. You see, by this one, you didn't succeed. You didn't really get anything if you simply use this one. But you asked Mathematica to subtract this and the expression you got with your brain and calculate out and simplify. Well, the difference is 0, which means these two are the same. In other words, if you know what you're doing, you can use computer algebra system to its full power. Remember, computer is your slave, not the other way around. Okay, enough warming up, and let's move on to a little bit harder type of problem. Finding out solution of complex equation. And all the problems, A, B, C, D, those are same type of problem. Z to the a certain power is a certain complex number. And I think we'll have time to do only one of them, so let's just do one. And then the others are all left at the exercises. Z to the 6th power is negative 64. And when I did this in class, one student immediately found out one of the answers. 2i, because 6 root of 64 is 2, and we need negative 1, so 2i. Is it right? 2i to the 6th power is indeed negative 64. Great, we have a solution, but this is a 6th order polynomial equation, so we need 6 solution. The question is, where are the other 5? So just guessing one solution did not work very well. By the way, that was not really guessing. It was educated guessing, and that was good. Well, let's go over to an alternative approach here. I'd like to save some time, so let me open up this new notebook. And we want to use De Moivre's theorem, right? So we have to start from the polar form. So let's express z as r cosine of theta plus I sine of theta. And then what we do, well, z to the 6th power is negative 64, so let's do it. Z to the 6th power is this one, because after all, z is r cosine of theta plus I sine of theta. We designed that way so that we have the polar form. Now, 64 has to be written in polar form as well. And in order to do that, I rewrote it as 64, which is the amplitude, the modulus, times -1. And we can express -1 in polar form with the angle pi, like this. Cosine pi plus I sine of pi, that's -1. Now, let's apply De Moivre's theorem. We have r to the 6th power times cosine of 6 theta plus I sine of 6 theta is 64 times cosine of pi plus I sine of pi, the right-hand side. Comparing the left-hand side and right-hand side, you can find out r value, the modulus, like this. R to the 6th power is 64. R is 6th root of 64, that's 2. How about theta? Well, comparing the left-hand side and right-hand side, we can conclude 6 theta is equal to pi. And what do you get? We have theta equal to 6 over pi. We got modulus and we got the argument. So putting everything together, we have the solution. R times cosine of theta plus I sine of theta, which is 2 times cosine of pi over 6 plus I sine of pi over 6. Consequently, we ended up with this result. Great! But one more question here. How many solutions do we need? We need 6 solutions because this is 6th order polynomial equation. We just found only one. And actually we found another one, 2i. So we found 2. What are the other 4 solutions? And what is the general way to handle it? Okay, let's scrap off this close and no cigar method. And let's go over to the answer key. Here, when we express 64, please note that adding 2k pi doesn't change anything. So let's put those plus 2k pi. Why? Well, that's going to be answered in a moment. And then we go to the same direction. R cosine of theta plus I sine of theta to the 6th power is equals to, well, the right-hand side with this plus 2k pi. And apply De Moivre's theorem. R to the 6th power times cosine of 6 theta plus I sine of 6 theta is equal to, again, the right-hand side. 64 times cosine of pi plus 2k pi plus I sine of pi plus 2k pi. Now, comparing the moduli, we get r to the 6th power is equal to 64. So r is 6th root of 64. That's 2. We have unique solution here for modulus, and that's to be expected. How about the argument? That's where this plus 2k pi is serving, doing its work. 6 theta is equal to pi plus 2k pi. So if I divide everything by 6, what do you get? Theta equal to pi plus 2k pi over 6. And this k value can be various. 0, 1, 2, 3, 4, and 5. You're going to get 6 solutions from those 5 k values. If you plug in k equals to 6, you're going to get the same result as k equals to 0 case, because that's the same as adding 2 pi. What is a typical trick? Plus 2k pi and then express both right hand side and left hand side in polar form. Apply De Moivre's theorem, and when we identify the argument, we get something plus 2k pi over n. And then plus k equals to 0, 1, 2, 3, all the way up to n minus 1. And we have all these values. So we have z equal to 2 cosine of theta plus I sine of theta, where the angle of theta will be these 5 values. Consequently, we have to have 6 solutions. Did I say 5? Excuse me. 0 and 1, 2, 3, 4, 5. So there are 6 theta values. Consequently, we are going to get 6 solutions. By the way, I just inserted a mathematical program to calculate all these values and simplify, and let's run it. And actually we have these 6 solutions. 2 times I over 2 plus square root 3 over 2, that's the first solution when k value is equal to 0. And case 1, case 2, case 3, case 4, and case 5, we have all these 6 solutions as listed here.